Hello everyone, welcome to Rail Signaling Academy. Today we are starting a new series on train detection systems. While the old series on headway will continue as it is, I will be starting different series in parallel just to keep the content diverse. Now the first train detection system that I will talk about today is axle counters. Why axle counters, you may ask? Well, it's because I feel axle counters are going to be more widespread in the future and will replace more and more track circuits than there are today. Now the agenda. We will be splitting this video into two parts, and today's video will only cover basics. We'll be talking about history of axle counters, then we'll be talking about principles behind axle counters used today, then we'll talk about how axle counting works, and then a little bit on a very high level architecture of axle counters. So let's get into it. Now, what is an axle counter? Well, as the name suggests, it counts axles. Literally, that's what it does. Axle counter counts axles. But what's important is that what it does with that information. So what it does is that based on that information, it determines whether a section is vacant or not. Let's look at the history a little bit. Now, in the past, axle counters were based on treadle-like mechanisms. Now, what treadles basically are that you see this box here. This box had a little arm connected to it, and then you see the wheel. The wheel has flange. Flange has a certain depth, and as the wheel went over this, the flange would press this arm, and this arm would actuate the electronics inside this box, and that would register whether the wheel or axle had passed over it. So the original axle counters that were used back in the days, and I think they are still in use in different places for different purposes. They required the train or the wheel to physically come in contact for actuation. But then the later developments, the ones that we use today most commonly, use the concept of electromagnetism for actuation, thereby resulting in a contactless actuation, which means that the wheel flange does not have to come into contact with axle counters anymore, and they're still able to actuate them. Therefore, they're less prone to damage. A glimpse of today's axle counters that use electromagnetic field varieties of axle counters, and in none of them the wheel flange has to come in contact with these. All wheel has to do is just pass over these, and the axle counters will register whether a wheel has passed over them or not. And that's exactly what we're going to look into in this video. Now, principles behind axle counters used today. I'll be taking a few steps back. I'll be talking about some concepts of electromagnetism, albeit I won't be going into too much detail. I'll only be talking about basic concepts that are extremely relevant just for axle counters. So let's look at the first concept. The first one is magnetic field lines around the magnet. Now, what really are magnetic fields? Magnetic field lines are imaginary lines around the magnet that represent the magnetic field. As you can see, it originates from North Pole, goes to South Pole. These are two different magnets. Originates from North Pole, goes to South Pole, originates from North Pole, goes to South Pole. One important feature of magnetic field lines is that they seek path of least resistance. Why it's important, we'll find out. Some practical experiments, if you want to visualize how magnetic field lines are, you can have a magnet and then you can sprinkle some iron core fillings around the magnet, and you'll see that the iron core aligns itself to the magnetic lines. Or you can have a compass. You can move the compass around the magnet, and you'll see that the compass orients itself to the magnetic field lines. The second concept that we need to know is of magnetic permeability. This is actually the most important concept. Now, what permeability is? The ability of a medium to conduct magnetic field lines through it, which means if the permeability is higher, that means they're able to conduct more. And if you remember from the last slide, I said that the magnetic field lines, they seek path of least resistance. And we can see in the diagram here, magnetic field lines go from north to south. This is air, but as soon as you introduce iron in there, you'll see the magnetic field lines immediately reorient themselves and pass through the iron core because they are seeking path of least resistance, and iron core has a much higher permeability. Why I'm talking about this is that all the materials that there are loosely categorized into three categories. One is diamagnetic, paramagnetic, and ferromagnetic. So diamagnetic are materials that have permeability less than unity, and they offer the most resistance. For example, copper. I think even wood is diamagnetic. Paramagnetic are materials that are a little higher than unity, which means they offer a little less resistance compared to diamagnetic. And then the ones that offer least resistance or the most conductive are ferromagnetic materials. This term is important because in the axle counter realm, you will see a lot of time vendors or suppliers say that we want the wheel to be ferromagnetic for our axle counters to be working reliably. So third concept is that in real axle counters, you don't have permanent magnets. Instead, you have coils because when you pass current through a coil, the coil acts like a magnet. And for experimentation purposes, you can do that too. Through a coil, try to pass current through the coil, put some iron fillings around, and you'll see the iron fillings orient themselves according to the magnetic field lines. Now let's look at an actual axle counter. So this is an actual axle counter, and inside the axle counter, there are basically two coils. One is the transmitter coil, one is the receiver coil, and you have magnetic field lines going from one to the other. However, the medium between those two coils currently is air. When there's no wheel, when there's nothing, the medium is air. But then, as soon as you have a wheel passing over these axle counters, you see that the permeability now is this number, which is for air. And then you also have permeability of 5,000, which is for iron. And what that means is that suddenly now you have a material that is super conductive compared to air. That means now the magnetic field lines are getting much more support to go from the transmitter to receiver. And that's exactly what axle counter records. It's the difference between your normal scenario where you have just air and when you have a wheel passing over where the magnetic field lines are getting much more support, where the magnetic field lines become much stronger, and where the magnetic coupling becomes the highest. Now, as you can see in real axle counters, it's not just one coil, we have two coils because we want to also be able to know the direction in which the wheel is going. And we'll look at that in the future slide. Now, axle counting and block occupancy or block vacancy. How does that work? Well, track is divided into sections using axle counters, and every section requires, so if this is one section, it requires two axle counter heads or two axle counter sensor to be able to compute occupancy and vacancy. And inside the evaluator or inside the computer or the processor, it maintains something called an in count and an out count. Now what happens? As soon as it steps onto the axle counter, if you can see the picture here, there are actually two sets of coils. So the first coil registers the change in magnetic field, then the second coil registers the change in magnetic field, and then based on that, the axle counter determines that a wheel has entered on the section. Now imagine for a second if there was only one set of coils, axle counter would know that a wheel has passed over it, but axle counter would not know which direction it's going in. So in order to calculate in versus out count, axle counter also has to know the direction of the wheel. So as soon as the wheel goes in, a block is considered occupied when in count is greater than out count. So now you have an in count of 1, out count of 0 because from this section no axle has exited. Only one axle has entered. Now on the next one, in count becomes 2 because 2 axles have entered. No axle has exited. Now you can see one axle has exited, and on this section, one has entered, none has exited. Now, as soon as in count becomes equal to out count, which is this one and this one, the axle counter knows that this section is vacant. Same thing happens here. It becomes this one also becomes occupied. This one remains occupied, and so on and so forth. That's how block occupancy and vacancy works. Now let's look at the architecture. Now there is really no single way to explain this since every manufacturer, every project could have subtle differences. But I will talk about what the architecture is like in general so that you get a sense of how a typical axle counter architecture is like. To start with, this is an example track. It's an empty segment where we'll be starting to place axle counters. Currently, there are no axle counter sections. So what happens is that signaling designers, along with coordination with other disciplines, they determine the appropriate track section lengths based on safety and based on normal operation, based on abnormal operation for some operational flexibility, and based on recovery scenarios or for fault tolerance. Signaling designers decide where to place the axle counters. Now, when we show axle counters on a line, what it really means is that you have a track, and on the track, you're placing axle counters on one side, and that's how it looks like. The next one is junction box. So I just want to go back again. Right now, we have only placed axle counters. In the next one, we'll be placing junction boxes. Now, what these junction boxes are, you'll see this all the time with axle counters. Now, different vendors have different types of junction boxes. Some of them could be very simple and could have just one cable coming all the way. They could have one cable coming all the way from behind. And then all this junction box does is that it splits into individual cables that are going into the coils. And some junction boxes could be a little more complicated. They could have extra electronics such as amplifiers, noise filters, etc. The only downside to having extra electronics is that junction boxes are on trackside, and trackside is very harsh. They have very harsh environments, so they are more prone to failure the more electronics you have on that. So now every single axle counter has junction boxes connected to them. All of those junction boxes have then cables running through a cable trench. I haven't shown cables from this one, but you'll basically be having same thing running through the other duct, or could be this duct. And all of those junction boxes then feed into axle counter evaluator boards. After that, you have multiple axle counters, which will all be talking to the interlocking. So that's how your interlocking, which is the brain, it ensures vital, safe train separation by talking to all the axle counters, and that's how interlocking knows which track section on the line is occupied and which track section is vacant. And based on that, it decides whether to set the route, whether to release the route. And so on a high level, that's how an axle counter architecture works like. Now, let's look at the recap. So today what we discussed was history and principles behind axle counters, how axle counters work, and then very high level architecture. So thank you, and thank you all. I'll see you in video number 2 of axle counters. Take care.